A system that can move among several states can be described by probabilities, and this lesson follows what happens when some moves are easier in one direction than in the reverse direction. The main idea is that an asymmetric rule for transitions can create a steady flow of probability around a network, even when the overall long-term probabilities stay fixed. The explanation begins by turning state weights into ordinary probabilities, then uses a Markov chain to show why this directional bias breaks detailed balance. The starting point is a collection of states, where each state has a weight, and the ordinary probability of that state is found by taking the square of the size of its weight. After those probabilities are collected into one probability vector, the entries describe how likely the system is to be in each possible state at a given step. A Markov chain describes step-by-step random movement among states, where the chance of the next state depends only on the current state and the transition probabilities. The transition rule is stored in a Markov kernel, which is a table of probabilities whose rows each add to 1 because the system must go somewhere after each step. When the probability vector is multiplied by this transition table, the result is the probability vector for the next step. A stationary distribution is a long-term probability pattern that stays the same after the Markov transition rule is applied. Even when a stationary distribution stays fixed overall, probability can still move between particular pairs of states in opposite directions. Detailed balance is the special condition where, for every pair of states, the stationary probability of being at the first state times the chance of moving to the second equals the stationary probability of being at the second state times the chance of moving back to the first. In words, detailed balance means that each two-way connection has no net flow, because the forward traffic and backward traffic exactly cancel. To create asymmetry, certain directed edges are chosen as forward edges, and each of these edges has a positive forward transition probability. The reverse transition is then suppressed by a factor called e to the negative lambda times aij, where lambda is positive and aij is positive, so the reverse move is smaller than the forward move. For one forward edge from state I to state j, the probability current along that edge is the stationary probability at I times the transition probability from I to j minus the stationary probability at j times the transition probability from j to I. Substituting the reverse transition rule changes that current into the transition probability from I to j times the quantity, the stationary probability at I minus the stationary probability at j times e to the negative lambda times aij. If the stationary probability at I is greater than the stationary probability at j times e to the negative lambda times aij, then the quantity in parentheses is positive. Because the forward transition probability is also positive, the whole current along that directed edge is positive. A positive current means that the stationary flow from I to j is larger than the stationary flow from j back to I, so the two directions do not balance. Since at least one forward edge exists, at least one pair of states fails the detailed balance equality. When all chosen forward edges satisfy the same positivity condition, the net probability current is a sum of positive edge currents, so it is strictly positive. The conclusion is that directional suppression of reverse transitions creates an asymmetric Markov kernel, breaks detailed balance, and produces a steady net probability current through the selected forward edges.